So up to now, what we're assuming is that interference can happen between executing one workflow. If you have action prefix A and then W, you can have anything happening between A and W. So that's why concurrency is actually possible. But now, if you want to analyze properties that concern about the states of the underlying system, we better somehow close the execution environments of our workflow execution. So let's say, if we have a trace T of A1 up to A10, we actually want to analyze what's the overall effects of executing A1, A2, A3 up to A10 without having any interference, and then to see if A1 up to A10 can actually complete. So this is actually different. This actually is a different assumption from the trace semantics and the operation semantics. So we actually try to forbid the interference in this case, in this analysis. And in order to do this, we define a new semantic function, which is called apply. So which will take a trace of a workflow, and that workflow can be a combination of, it can be a parallel composition of several workflows. So this really models the real scenario, because we might have several workflows executing in parallel. And then from that traces, we can actually get a state transformer to see what's really the effects between the before and the after. So let's see what we can do with this relational semantics. So now, we are actually in a ready position to formalize the analysis objective, as I just mentioned before. Again, the analysis objective is, can the parallel composition of W1 up to Wn be safely executed together? Can it complete? That's our key concern. And to actually formalize the objective, we have to use the trace semantics and the relational semantics. That's how we can do it. First of all, we define this notion here to denote the set of successfully terminating traces because it has a check mark at the end of the trace, like in CSV. And the second notion denotes the set of traces that is possible after executing a particular trace of W. So for example, if W is actually A, and then B, and then C. So after executing A, you still have B and C that is possible after executing A. So that's what this notion means. And now, we can actually formalize under what circumstances can workflow can complete. Right? So this is to say, given the trace of W, we can actually calculate the effects of T, which will transform from the current state sigma to an intermediate state sigma prime. So this is the first transformation. We want to make sure there is at least one way to actually transform from sigma prime up to the end of W. So these two transformations have to respect the apply function. So that's why we actually need a relational semantics, and we have to close the execution environments when we do the analysis, making sure there's no interference in the middle. Finally, we can actually calculate this particular notion of precondition for workflows, which means every time we have a workflow, whether it's actually a parallel combination of several workflows or just a single workflows, we can actually calculate exactly when this workflow should be called, such that once the workflow is launched for execution, it can be guaranteed to complete. Okay? Right. So now, for the rest of the talk, I will just want to guide you through very quickly on an example on the paper. So just to give you some idea that our approach can really be applied in the real world. So the syntax I present on the slide is actually used in our laboratory. So we actually use this syntax to generate our current website for the Oxford University Computing Laboratory. So this is a language for guarded transaction. As you can see, we have several classes. In the class, we have attributes and we have methods. And for each individual method, which is highlighted in red, we actually use predicates to specify precisely the precondition and postconditions for your intent and when you should call the methods. And what's going to happen is we have our automatic compiler, which will compile these predicates into the guarded substitution language as in Professor Adriel. And then part of my thesis is also to look at how you can translate the guarded substitution language into a SQL database, and also to prove that the translation is correct. So this is really happening. This can be used. So in this hotel booking example, we have reserve. We can reserve the room, we can cancel booking, and etc. etc. And of course, we can actually characterize what should be the precondition for individual method. For example, if we want to allocate a room, we better make sure there's at least a room available for the days that you want to book. And we have other methods as well, and we also have more than one class. We have reservation class, we have allocated class, and we have different methods for different classes. Right. Now, we can define actually workflows on top of the guarded transaction. And we are using exactly the same syntax as defined before. The difference is what we just presented was the abstract syntax. And this is the ASCII concrete syntax for the compiler to do any automatic translation into some execution-oriented language like detail or other constructs for execution. So in this case, we can actually characterize what should be the precondition for your workflow. So very briefly speaking, because you want to allocate a room eventually, so you better make sure to complete your workflow, before you execute your workflow, you have to make sure that at least the dates you are going to request are available in the beginning of the workflow. So, right, I'll go very quickly to finish the talk. Right, so there's another workflow which will also allocate a room. So it actually has the same precondition as the previous workflow. They have the same precondition. However, you cannot apply the same precondition for executing the two workflows in parallel. It got to be something stronger. So it has to be the case that there are actually two rooms available at least, such that the dates can fulfill the request for each individual workflow. So that's a general idea, right? So this is a trace for our system execution. So after this trace, we actually need to allocate two rooms. So if this precondition is already satisfied before we run a parallel combination of the two workflows, this will make sure after this point, the system wouldn't really block any of the two workflows. So that's exactly why we have this formal approach to characterize the preconditions for workflows. Right, to conclude my talk, so in this talk, what we have presented is a new workflow language, and we upon the guarded transaction, and we present different semantic views for the workflow language. And what really makes our workflow language unique or novel is that the events do not represent the synchronizations between workflows. They are not shared. And the final point is actually the crucial point. What we really want to say in this talk is that this approach, although it's formal, but it can really be applied in the real world. Because as you can see, we got concrete syntax for our guarded transaction language, and we have concrete syntax for the workflow. And usually, in our case study, workflows, the patterns of workflows are actually simple. They are not really complex. And the interference between workflows are actually not that common. And also, the effects of transactions are usually deterministic. So to actually calculate the preconditions for workflows or for transactions, it is not that difficult. So this approach, although it is general, but if you apply to a specific domain of information system, it can really work well. Thank you for your patience. That's it. Thank you.